Hi students, നമ്മൾ കഴിഞ്ഞ ക്ലാസ്സിൽ invertible linear operators form an open subset of L of Rn എന്ന് കണ്ടു. And inversion is a continuous mapping in that subset. ഇന്ന് നമ്മൾ കാണാൻ പോണത് matrix of a linear transformation. So നമ്മൾ Rnൽ നിന്ന് Rmലേക്കുള്ള linear transformations ആണ് കൺസിഡർ ചെയ്യുന്നത്. So രണ്ടിൻ്റെയും സ്റ്റാൻഡേർഡ് ബേസിസ് നമ്മൾ എടുക്കുന്നു. And suppose a linear transformation, you know how to represent it by an M/N matrix with respect to this given basis. അതിലേക്ക് ഞാൻ കടക്കുന്നില്ല. Suppose the matrix of that linear transformation A is matrix Aij. That means A11, A12, etc. A1n, A21, A22, etc. A2n, etc. etc. AM1, AM2, etc. AMN. Suppose that this is the matrix of A. Now you choose any vector x equal to sigma Cj Ej in Rn, where Ej is the standard basis of Rn. So x is Cj Ej, sigma Cj Ej, and A is represented by the M/N matrix Aij. Then look at the vector Ax. It is a vector in Rn, for x in Rn. So what are the coordinates? The ith coordinate of the vector Ax is sigma over j Aij Cj. So here j running from 1 to n, and for all I equal to 1 to m. This much we know. And suppose we have two matrices A and B. Their matrices, you have two linear transformations A and B, and suppose their matrices are matrix Aij and matrix Bij respectively. Then the matrix of the linear transformation A plus B will be precisely the matrix Aij plus Bij, which is equal to matrix of A plus matrix of B. Similarly, if small c is a scalar and A is a linear transformation from Rn to Rm, then look at the linear transformation Ca from Rn to Rm. It will be represented by the M/N matrix Caij. And another thing, suppose you have two matrices, two linear transformations, A from Rn to Rm and B from Rm to Rk. Then look at Ba. B is a linear transformation from Rn to Rk. So what is the matrix of the linear transformation Ba? You can show that it is precisely the matrix of B into matrix of A. These much things we know. I have not written these things in this slide. Now I want to explore the relation between matrix of a linear transformation and the corresponding operator norm. Remember what is operator norm? Operator norm of A belongs to L of Rn, Rm is norm of A equal to supremum of norm of A of x, such that x varies in Rn, norm x is less than or equal to 1. And we have a famous inequality which we'll be often using. What is that inequality? Norm of A of x less than or equal to norm A times norm x for all x in Rn. Now I want to estimate the operator norm of A in terms of the matrix of A. So we start with the vector Ax, where x is equal to sigma Cj Ej in Rn. Look at norm square. So what is norm square of a vector? Summation over the square of the coordinates. That is the norm square. So this is the ith coordinate. So summation over the square of the coordinates. So that is norm of Ax square. Now you apply Cauchy-Squart's inequality, which we have mentioned in a previous class. So Cauchy-Squart's inequality says that the bracket square, that is less than or equal to sigma over j Aij square into sigma over j Cj square. Then summation over I. Remember Cauchy-Squart's inequality? What is that? Sigma over j xj yj whole square less than or equal to sigma over j xj square into sigma over j yj square. So if you apply Cauchy-Squart's inequality to this bracket square, you will get this bracket. Then sigma over I, that is carried over here also. Now look at this term. This is independent of I. So this can be taken out here, and again it can be taken out here outside sigma over I. So what is sigma over j Cj square? That is precisely norm of x square. So norm of x square into sigma over I comma j Aij square. So this is what I get. Norm of Ax square is less than or equal to sigma over I comma j Aij square norm x square, which is again less than or equal to sigma over I comma j Aij square for all x in Rn with norm x less than or equal to 1. Therefore, sigma over I comma j Aij square is an upper bound sigma over I comma j Aij square whole to the power 1 by 2 is an upper bound for the set of all norm of A of x such that x varies in Rn norm x less than or equal to 1. But what is the least upper bound? What is the least upper bound? It is precisely norm of A. And you compare the least upper bound and that upper bound. So you will get least upper bound, namely norm of A less than or equal to sigma over I comma j Aij square whole to the power 1 by 2. Hope you understood. Mark it as 1. Now in 1, what is 1? This inequality. Instead of A, you replace it by A minus B or B minus whatever. Then what I will get? So what is the matrix of A minus B? It is matrix of A minus matrix of B. So in 1, replace A by B minus A. We see that if the matrix elements are continuous functions of a parameter, then the same is true of A. So what is the meaning of this statement? So let us replace A by B minus A in 1. So what I will get? Norm of A minus B less than or equal to sigma over I comma j Aij minus Bij whole square whole to the power 1 by 2. This is what I get. Norm of A minus B less than or equal to sigma over I comma j aij minus bij whole square whole to the power 1 by 2. Now suppose that instead of this matrix aij, my entries, they are functions of some parameter p. That means a11 of p, a21 of p, etc., a1n of p, etc., etc., am1 of p, am2 of p, etc., amn of p. So we have mn functions. Functions are called by aij. So suppose that is the situation. Then norm of a minus b less than. So a depends on p. B also depends on p. So a will be denoted by a suffix p, b will be denoted by b suffix p. So norm of ap minus bp less than or equal to sigma over I comma j aij of p minus bij of p whole square whole to the power 1 by 2. This is what. So we are going to explore what is the meaning of this statement. Instead of real numbers a11 etc. amn, suppose I have mn functions a11 of p etc. amn of p. They are all continuous. So to say continuity, you need some metric space kind of object. So start with a metric space yes, and you have mn functions a11 etc. amn defined on S, and all these functions are real valued functions and they are continuous on S. Understood? Now for each small p in that metric space S, a suffix p is the linear transformation of Rn into Rm whose matrix has entries aij of p. That means you fix a point p in S, correspondingly you will get a linear transformation ap from Rn into Rm. Some other person fix some another p in S, that person will get some another linear transformation from Rn into Rm. So that linear transformation depends on the point fixed. Understood? Therefore call that linear transformation a suffix p, where p is the point fixed in S. And since this is a linear transformation, it has a matrix, n by n matrix, and they are given by these functions aij of p. The linear transformation is given by these functions aij of p. Then look at the mapping p going to ap. From where to where? P is in S, ap is in L of Rn comma Rm. Look at the mapping p going to ap from S into L of Rn comma Rm is a continuous map. Is a continuous map. Why continuity? It is because of inequality 1. So what is inequality 1? Let us again go through inequality 1. This is inequality 1. So inequality 1, first I am replacing a by b minus a. Then again I am replacing a by ap and b by bp. So what I will get? Norm of ap minus bp less than or equal to sigma over I comma j aij of p minus bij of p whole square whole to the power 1 by 2. So this is precisely, so the thing is that if okay, one more thing. Here instead of a, I will replace it by ap first. So what I will get? Sigma over I comma j aij of p square whole to the power 1 by 2. Now you take 2 points p and q, small p and small q in the metric spaces close to each other. So correspondingly you have the linear transformations AP and AQ. So what is AP? Sigma over I comma j. So norm of AP less than or equal to sigma over I comma j aij of p square whole to the power 1 by 2. What is AQ? Norm of AQ less than or equal to sigma over I comma j aij of q whole square whole to the power 1 by 2. So norm of AP minus AQ less than or equal to sigma over I comma j aij of p square minus aij of q square whole to the power 1 by 2. Now, if q is close to p, then aij of p is close. Aij of q is close to aij of p. So, modulus of this can be made as small as you want. So, sigma over I comma j can be made as small as you want. Whole to the power 1 by 2 can be made as small as you want. That means norm of AP minus AQ can be made as small as you want. That means AQ is close to AP. So what is the conclusion? If Q is close to P, then AQ is close to AP. This is precisely continuity. Continuity precisely means when the domain points are close, their images must be close. So this is precisely continuous. This mapping P going to AP is a continuous mapping of S into L of Rn, Rn. Hope you understood. Thank you.